Okay, you're most welcome back, and I think I'll start the topic very soon, and I think I'll just change for the moment and just look at you in person. Thank you very much. We're going to look at an area called probability. Probability is a really interesting part of the course. It's one that a lot of people do a lot about afterwards as well. It's linked to statistics. We see it in the pandemic, and people say, what's the probability of this or the likelihood of that, particularly with things spreading and all that. So probability is out there in a lot of fields, not just betting and various things as well, but it's huge in the stock exchange and various returns on lots of things. But when it comes to the Leaving Cert questions, the questions deserve a little bit of thinking before you answer, in that the questions themselves are generally very quick to answer, as long as you've done your background thinking correctly. You'll find the answers can be quite short. You can almost write down the answers for some of the questions. Just call out the answer really in a way if you know what you're being asked. So what I'm going to do is I'm going to go through some of the, I'm going to go through the probability section, but I'm going to show you how some of the key questions you've got to ask to say, is this probability depending on another one? Is it independent? Is it conditional? And how you identify those things. Is the order important or not? Or when it comes to statistics, are we talking about the standard deviation or the standard error of something? Is this a characteristic of sample, or is it individual values we're interested in? So really, I'll go through some examples now, but just it is a topic that's very accessible, very easy to do very well in, and we just thought we'd just go through it now with you. So I'm going to start by going to the probability section, and thank you very much for your attendance today. So hopefully you've got the notes there. It's a note section on probability, and we'll start now with, I just want to clear my screen. Okay, probability. So there's some terminology. I'll be going through this very quickly in various topics, and then much slower when it gets to the harder bits. So probability is how likely something is. If something is impossible, we say it's 0. If it's certain, we say it's 1. Or if it's somewhere in the middle, we use 50-50. Very unlikely up to very likely. So the sun will shine sometime today. Well, it has. But what's the probability that you will win the lottery next year? That there will be 367 days in the year? Or if you plug your TV out, it'll stop showing the program, or it'll rain sometime next year. I think there are questions you could ask, but the sun will shine sometime tomorrow or today. I think probably it could. Or in all cases, the likelihood of happening is given somewhere between 0 and 1. It could be as high as 1, could be as low as 0, but it won't be higher than 1 or lower than 0. So the sun will shine sometime today. Yeah, that's possible. You will win the lottery next year. It's unlikely, but it's not 0, as long as you buy a ticket. There'll be 367 days next year. Well, that's impossible because there won't be. If you plug your TV out, it'll stop showing the program. I reckon it will. That's a 1. And it'll rain sometimes next year. Well, it's conceivable that it wouldn't, but it's very likely that it will. Okay, when an operation is conducted, the results are called outcomes, 30. And the possible outcomes for throwing a die are 1, 2, 3, 4, 5, and 6. If a bag is filled with 27 red, blue, and green counters, the possible outcomes are red, green, or blue if you pick one. And the possible outcomes when selecting a card suit from a pack are spade, club, hearts, and diamonds. So from a formula point of view, the probability that an event meets a particular condition is given by PE, is the number of outcomes meeting it over the possible number of outcomes. So PE is that. P not E is that it won't happen, and that represents the other possibilities. And the probability of something happening plus the probability of it not happening must equal 1. because either it happens or it doesn't, and that's the total set. So the probability V, or the probability of not E, equals 1. Start with some questions. Write down the sample space relating to the following events. Tossing a coin. Will you either get heads or tails? Rolling a die, 1, 2, 3, 4, 5, or 6. Or selecting a pack of cards. There's a whole load of examples there. You've got the ace of clubs, 2 of clubs, 3 of clubs, ace of diamonds, all the way up to the king of hearts. So you've got 52 different options there, where C represents clubs and they're the honor cards. So let's see if we also understand probability an awful lot more than we give ourselves credit for, and sometimes when we see the formula it can put us off. So I'm going to ask these questions now first without the formulae and see if we get them right. If I roll a die, 6 sides to it, what's the chance of getting a 1? What's P1 on the roll of a die? I'd say most people would say 1 in 6, because there's one way of getting a 1 and there's 6 ways in total. What's the probability of an even number on the roll of a die? Well, even numbers are 2, 4, and 6. There's 3 of them. So I would say the probability is 3 over 6, or a half. It's either even or odd. What's the probability of an odd number on the roll of a die? Well, odd numbers are 1, 3, and 5. There's 3 of them. 3 out of 6, or 1 out of 2. Again, either odd or even. What's the probability of an even number or a 1? An even number or a 1 would be 2, 4, 6, or 1. And there's 4 of those, over 6, or 2/3. What's the probability of an odd number or a 1? Well, an odd number is 1, 3, and 5, or a 1. We've already counted the 1. So it's 3 over 6, or 1 over 2. So what we're finding in the last one there is that even though we said or, it didn't increase the probability at all. Or didn't make it any better. Now, it didn't make it any worse, but it didn't make it any better. Whereas in this case, or 1 meant that it did make it better. So in this case, 1 was not an even number. So it couldn't have happened at the same time, whereas 1 and odd were even numbers. So we have to see whether they overlap or not. So the sample space for the roll of a die is given as 1, 2, 3, 4, 5, 6. Given that the probability of a 1 is just one way of doing it over the total number of ways, that's 1 over 6. The even number gave us 3 ways. The odd number gave us, again, that should be 1, 3, and 5, sorry. That's 3 over 6. And the even number should give us 2, 4, 6, and 1. And this, we didn't add the 1 to it. So there are the answers there on that page. Now, a card is drawn at random from a pack of cards. Find the probability that the card is either a queen or a club. So we look at the clubs first, and there's 13 of those. We look at the queens, and we say there's a queen of spades, diamonds, and hearts, and clubs. We've already counted the 1 in the clubs. So in this case, they're not independent in that sense. They can be the same. So the queen is there and there. We calculate the probability of the number of outcomes meeting the condition over the total number of outcomes. Now, there were 13 clubs and 4 queens, but 1 was both. So there we can see that the queens, that there's 4 of them, but 1 of them is the queen of clubs. And there's 12 clubs plus the queen. And this one, we don't want to count it twice. So the total number of outcomes for the queen and the clubs are 13 clubs plus the 3 others. So the clubs or queens turns out to be 16 in total, or 8 over 26, or 4 over 13. Now, We turn to a topic called mutually exclusive. Mutually exclusive is when if it's A, it can't be B or something like that. So if I'm an odd number, I can't be an even number. If I'm a 2, I can't be a 6 or something like that. So let's look at those. And that's where we noticed as well on mutually exclusive, when we said probability of even or a 1, I can't be even and a 1. So they were considered to be mutually exclusive. Mutually exclusive outcomes are said to be mutually exclusive if they cannot both happen at the same time. So when choosing a pack from a card, I can't choose clubs and spades at the same time. But it could be a king and a black card. So kings and black cards are not mutually exclusive, but clubs and spades are. So very often in the question, we've got to look at it and think about it and say, are they mutually exclusive or not? Because different answers and different equations can apply. So let's start. In cases of mutually exclusive outcomes, OR makes things easier. So an even number or a 1. The 1 there adds to the even numbers because they're mutually exclusive. So the probability of A or B is the probability of A plus the probability of B. Or if we write it in set notation, P, A, or B is A plus B. In cases where they're not mutually exclusive, or can make things easier, but not necessarily, for example, odd number or a 1, didn't make it any better. So here we say the PA or B is PA plus PB minus the bit in the middle, PA and B. Or in set notation, PA union B is PA plus PB minus the intersection. So if we think about it, if we go back to the queens, and I think there were queens and clubs, the probability of clubs, I think, was 13 clubs out of 52. The probability of queens, there were 4 of those, 4 over 52. But when we added them up, queens or clubs, we didn't get 17 because queen and clubs, club and queen, or queen of clubs, there was 1 of those, 1 over 52. So what we found was the probability of clubs might be 13 over 52. This might be 4 over 52 minus 1 over 52. So that's how that worked. Or if we remember the Venn diagram there, if we want to join the two, we can add up all of A, all of B. But if we add up all of A, we've got this bit here. If we add up all of B, we've got this bit here. So then we better take the bit in the middle from it, because we've counted it twice already. Now, PA and B is given by the probability of A by the probability of B given A. B given A. On the basis that A is known, it is, say, an even number. What's the probability it's a 2? Or what's the probability, if it's an even number, that it's a 1? Well, it won't be a 1 in that case. So that's what that given means. Means the probability given A. Given that you know the bit at the end, what's the probability of the first bit? Or written in probability set notation, PA intersection B is PA by this. And that's an important formula that we keep, because there's different ways of writing that. We could, for example, decide to write that as PB given A equals PA intersection B over PA. All I've done is I've taken that to the other side. So again, here we're seeing that that's another equation, and we'll hold that. It's in the tables, but I think it's important that we just keep that and know what that formula is and how we can manipulate, because you might need that in a question later. So let's see how mutual exclusivity works when we start using this formulae rather than just answering off, from a gut. What's the probability of an even number or a 1? What's the probability of an odd number or a 1 on the roll of a die? And here's the sample space. Okay. Well, even number or a 1, we say the outcomes are even. Even and 1 are mutually exclusive. You can't be both even and 1. So the special rule would apply. We'd say the probability of even or B would be PA plus PB. The first rule would apply. You don't have to do the other one. Therefore, we get P even or 1 is P even is 3 over 6 because there's 3 of them. 1 is 1 over 6 and we get 4 over 6. And that's our answer. P odd number or a 1. The outcomes are not mutually exclusive. So therefore, we're going to use the general rule. So P odd or 1 is P odd plus P1 minus P odd and 1. So P odd and 1, well, the probability of something being odd is 1, 3, and 5. So there's 3 of them. 1, only one way, 1 over 6. Minus, what's the probability if it's odd and 1? Well, that's 1 over 6 because there's one way of doing that. And that's the answer. Now, a card is drawn at random from a pack of 52. Find the probability that the card is either a queen or a club. Again, we're looking at this and we're saying the queens and the clubs. We calculate the formula. We can see there and we can use the, are they mutually exclusive? They're not. And because they're not, we use clubs or queens minus clubs and queens. So the 13 plus the 4 minus the bit in the middle. And that's how we got that. So I just did those questions twice, showing that you do it off the top of your head and get a feel for it, or you can use the actual formulae that are there. So total number meeting the condition PA or B is PA plus PB minus PA by PB given A. So the probability that it's A, which is clubs, is 13 over 52. The probability that it's a queen, 4 over 52. What's the probability that it's clubs? 13 over 52. And what's the probability that it's a queen given that it's clubs? Given that it's clubs, what's the probability of queen? Well, there's only 1 in the 13. So that's the 1 in 13. And that's how we get that P given A. And that's our formula. So you can either see it or work it out in your head, or else say, no, that's the formula that I should formally use, because they are not mutually exclusive. Okay. What else can they ask? Well, this section here, they talk about probability and they talk about sample spaces. Sometimes they draw these as tree diagrams as well. So let's look at the probability and sample spaces. Let's use the word and. When one operation has m possible outcomes and a second one has n possible outcomes, the total possible outcomes is m times n. And we'll show that in a moment. So these are sample spaces for somebody having a lunch. A 2-course lunch offers a choice of 3 starters and 4 main courses. How many different combinations are there? So 3 starters and 4 main courses. Well, for the starters, you could have starter 1, starter 2, or starter 3. And for the main courses, you could have M1 to M4. So you could have starter 1 and main 1, starter 1 and main 2, and there's no reason why you couldn't pick any main with any starter. There's no distinction there. So given that they're independent in that way, you don't have to have fish in both, or meat in both, or vegetarian in both, or whatever. So we can say S1, S2, S3, and for each of these you have 4 options. So if they're independent, basically you just have the number of them will be just one by the other. So they're A and B. And the same if you had 3 options. So if somebody said, what's the probability that you took starter 1, main 2, and dessert 3? Well, it's the probability that you took starter 1 by the probability that you took starter 2, by the main 2, by the probability that you took dessert 3. Because they're independent. If they're saying that it doesn't matter which one you take, having taken the first one. So here we go with the probabilities. A 2-course lunch offers a choice of 3 starters and 4 main courses. What is the likelihood of a diner choosing starter 3 and main 4? Starter 3 and main 4. Well, here are all the outcomes. If you were asked to draw the sample space, you would just write it all out like this. So we're looking for the probability that it's starter 3 and main 4. I don't think that's in any other place there. And there's 12 in total, 4 by 3, and there's only one that meets it. And that's how we would do it, by drawing them out like that. Or we could have done it by doing a tree diagram as well. We'll move on to a different example now. We'll do it by tree diagrams. If a restaurant offers 3 starters, 4 mains, and 4 desserts, how many different lunch selections can a diner choose? So here we've got starters 1, 2, and 3, mains, and desserts. Sorry, I just got a call there. I was just making sure that everything was okay. But hopefully you can hear me. There are some people helping me in the background just to make sure that everything's okay. But I don't think I've got a particular text that you can't hear me or anything like that. So I'm going to continue if that's okay. Representing the options as a tree diagram, I could say with starter 1, I could go and choose any of the 4 mains. Similarly, I could do that with starter 2 or starter. And with starter 2, again, I could do that, or starter 3, etc. Now, I could go then and I could print from main 1, I can go to pick dessert 1 or dessert 2 or dessert 3. So the whole thing becomes, quite a lot of a network in the end. I'll just go to the end of these and I'll show that in the end you've got something like this. You've got a whole load of lines from starter 1, from starter 2, from starter 3, all the way to dessert 3. So the question is, how many different options are there? Well, I've 3 here. And I've 4 here, and here I've got 4 as well. So 3 by 4 by 4, I've got 48 different options, 48 different lines there in that sense. I can take the starter 1 followed by a cross all the way. So I can go starter 1, main 2, dessert 3, etc. What is the chance of a diner choosing a particular lunch combination? Starter 2, main 4, and dessert 1. Well, the probability of starter 2, I'd have to look and say how many starters are there? 3, so that's 1 in 3. What's the probability of main 4? There's 4 of them, so it's 1 in 4. And desserts, I can see 4 of those, 1 in 4. So it's 1 in 48. And again, we're looking at a simple tree in that they're independent. I can choose any main after any starter. So what is the chance will the designer do it? I can see here that the choice of starter 2, a third, choice of main 4, a quarter, choice of dessert 1, a quarter, and that's how it's done. So that's another topic that you can get asked. So let's move up a little gear now and see, we look at another topic called expected values. Expected values are where there are several outcomes to the possible game or an event, and you've got to work out on average what might happen. So these are called expected values. It looks that there's a nice formula there, but it's actually not that tricky in the end. A game consists of rolling a fair die. Depending on the outcome, the following payments are made. So basically, you're going to roll the die, and it looks like there are 3 possible groups of outcomes. In the first outcome, and you can draw this by a tree by starting with the node like that, and just say the first outcome is that you get a 1. The second one is you get 2, 3, or 4. And the next one is that you get 5 or 6. Now, given that this is a die, you can say, what's the chance of getting a 1? And you might say it's 1 in 6. What's the chance in getting a 2, 3, or 4? Well, there's 3 options. That's 3 over 6. And the chance in getting 5 or a 6, that's 2 over 6. So if you get a 1, the payment you're given is 0. So you get nothing for landing a 1. If you land 2, 3, or 4, you're told you get a payment of €8. And if you get a 5 or a 6, you're told you get €15. What is the expected value from the game? So if you only play it once, you're going to get either 0 or 8 or 15. But if people play it again and again and again, on average, you'll see that they get a certain score. And you might want to, get that ready if you have to end up paying for the outcomes. So what we do here is we take each of these and we say, well, we've 1 in 6 chance of nothing, 3 in 6 chance of 8, and 2 in 6 chance of 15. And we add those 3 up separately. We say it's 1 over 6 times nothing, plus 3 over 6 times 8, plus 2 over 6 times 15. And the reason we can add them is that they're mutually exclusive. You can't get a 1 at the same time as you're getting a 2, 3, or 4, or at the same time you're getting a 5 or a 6. So we worked that out. So the formula is the sigma, the sum of each of these values by the probability. So the probabilities here, 1 in 6, 3 in 6, and 2 in 6. And that's the amount of money. That's your X value here. So when we put it together, we can say getting a 1, no money, 1 in 6 chance, contribution is 0. 2, 3, or 4, €8. 3 in 6. 3 in 6 is a half, and a half of €8 is €4. 5 or 6, half of 15, we end up with, but 5 or 6, but we've only 1/3 chance of getting it. So 1/3 of 15 is 5. So if we add the 3 of those together, on average, we can expect on this game to get €9. So for example, if it cost €10 to play, you'd get some return because on average you'd be giving back 9, and some people would say 15 wouldn't be bad return. I'll only lose €2 generally. I'd be very unlucky to lose it all. Okay. We now look at some formulae and terminology in probability. There's a lot of this, and we have to be very careful when we're reading the questions to say, what precisely are they saying? Are they saying, is that thing dependent on that? Are they saying, is that thing, is that combinations or is it permutations? So we just have to be sensitive to the questions. But once we have it, it's really a question of writing down the answer. So just bear with me on the terminology. It's important to get this right. The first terminology we're talking about is independent events. In the case of 2 events, if the outcome for the first event does not affect the outcome for the second, then the 2 events are independent. For example, a deck of cards contains 52 cards. A card is selected at random and put back before a second card is selected. The probability of finding a particular card on the second is not influenced by what happened on the first. Now, what's happening there that's really important is and put back. So you've got a pack of cards. Somebody says, pick a card. Okay, put it back. And then you ask the second person to pick a card. The second person can pick any one of the 52 cards. The other card is not gone. So we're saying they're independent. The second person's choice is independent of the first. So let's look at this. A deck of cards contains 52 cards. The card is selected and put back, and a second is selected. What is the probability of getting a club followed by a red? So you want a club first and then a red. Well, we start with the club. And that equation said how many meet the condition? 13 over 52. There are 13 clubs over 52. That's 1 over 4. We put the card back. What's the chance of the next one being a red? Well, there are still 26 red cards in there, so it's 1 over 2. So the chance of getting this and this and this means that and makes life tougher. So it's 1 over 4 by 1 over 2. Because it's this and this. Conditional dependent events. In the case of two events, if the outcome for the first event affects the outcome, then they are dependent, not independent. If a bag contains 3 apples and 3 oranges, the likelihood of an apple selected first is 3 out of 6. Okay, so there are 3 apples in there and 3 oranges. If the first fruit selected is an orange and is not replaced, then the likelihood of the second fruit being selected rises to 3 out of 5. So if you've got 3 apples and 3 oranges, and you pick one, you pick one at random, you have 1 in 6, well there's 6 in total, so you have 3 in 6 chance of being an apple. But it says here, if the first fruit is an orange, and you're down now to 2, the next time you're picking out, you have 3 in 5 chances because there's 5 fruits and 3 of them are apples. So let's look at how that condition, that will apply. A bag contains 3 apples and 3 oranges. 2 fruits are chosen without replacement. So what you're finding now is that very often you just pick the question up quickly and get on with it. But with probability, you have to go back all the time to the actual question and saying, was there a with replacement? Was it without? What were they looking for? Were they independent? Were they mutually exclusive? What are they telling me? So it's all in the language. So what's the probability that the first fruit is an apple? Well, there's 3 in 3, 3 apples out of 6, 1 in 2. The probability that the second fruit is an orange, knowing that the first is an apple, is the number of outcomes meeting the condition over the total. There are 3 oranges remaining out of a total. 3 of the fruits satisfy. Probability that the next is an orange is 3 over 5. What's the probability that the apple first and orange after apple? And makes life more difficult. So the probability of the apple first is 1 over 2 times 3 over 5, 3 over 10. So it's we picked the apple first, and at that stage the probabilities changed because we had 3 left for the orange. Okay. Combinations and permutations. Hope you find this clarifies a lot of the questions you get asked about committees, people on it, choosing boys and girls and women and men and various gender quotas or age quotas or whatever. It all comes down to whether we're interested in combinations or permutations. So let's look at this for the moment. There's some formula here as well, and the formula, a new symbol that we are seeing, is a thing called factorial. Factorial 3 is 3 by 2 by 1. Factorial 2 is 2 by 1. So let's look at the definition. The definition of a factorial for n factorial, and n is an integer value greater than 0. Or, yeah, 0 or greater. N factorial is n by n minus 1 by n minus 2 all the way down. So for example, 5 factorial is 5 by 4 by 3 by 2 by 1. 1 factorial is defined as 1, and naught factorial is defined as 1. With combinations, the order is not important. Unimportant, not important. A selection of a number of objects in any order, selecting or objects out of a total of n. That's a formula that you're given. NC or, often written as NR, n factorial over n minus r factorial or factorial. This is a really, really useful formula page. It's in your tables, go keep it, etc. This one isn't there, but it's equally useful. Permutations, the order is important. It looks like the first one. It's called NPR, where permutations are involved. The order is important. And it's n factorial over n minus r factorial. In fact, it's virtually the same, but this bit here is missing. The r factorial is missing. So you don't have r factorial. So you're not dividing by r factorial. So you're not dividing. So therefore, this is typically larger. There's more permutations and combinations, unless, of course, r factorial is 1. But if r was 2 by 1 or something like that, you'd find there'd be more permutations than combinations. So we'll keep that as another formula as well. Useful to write that down, useful to have it. It's a way of solving a lot of questions. Now, what I want you to do more than anything else on this question is just to think about how you would break it down and say, what's really going on here? Okay? How do I find out what the answers are? Okay. You have 4 very close friends. Well, you're probably hundreds, but but let's imagine that these are the ones that you're closest to. You get 2 tickets for a concert and you would like 2 of your friends to come. How many ways can you allocate the tickets? And I'm going to call them Adam, Brian, Kira, and Donna, A, B, C, and D. How many ways can you get rid of the tickets? You've 2 tickets, 4 friends. Well, Adam and Brian would be one option. Adam and Kira, Adam and Donna, Brian and Kira, Brian and Donna, and Kira and Donna. And that's the full set of samples. You've got A, B, AC, AD, BC, BD, and CD. There's only 6. The order doesn't matter. If you give Adam and Brian a ticket, it's the same as giving Brian and Adam a ticket. AB is the same as BA. 2 tickets to a concert, you'd like 2 of your friends to come. How many ways can you allocate the tickets? So using the formula, you say 4 friends, 2 tickets. It doesn't matter who gets the tickets. They're both equally welcome. Well, Brian could say, I got mine first. Look, just relax. There are 2 tickets. You're both going. It's okay. So the way that works is you'd say there are 4 friends. I have 2 tickets to give. And it's combinations. So the answer is 4C2. 4C2 is this, 4 factorial over 2 factorial, 4 minus 2 factorial, 4 by 3 by 2 by 1, over 2 by 1 by 2 by 1, 24 over 4, I get 6. That is the correct answer. That's how you do it. You say, how many tickets are there? How many have I got to get rid of? That's it. Oh, sorry, how many friends have I got? How many do I want to choose? Now, you've 2 gifts that you wish to give to friends. The first is a music voucher and the second is a travel voucher. Somebody gave you a music voucher for Spotify or for whatever, it doesn't matter. And the other gave you a travel voucher. How many different ways can you allocate these amongst your friends? Well, in this situation, one is a music voucher and one is a travel voucher. They're different. So if you're going to give Adam the music voucher and Brian the travel voucher, that's different from doing it the other way around. So really what's going here is that AB is not the same as BA. If you're counting the music voucher first. In one case, Adam gets it. In the other case, Brian gets it. So assuming that the pairing starts with the music voucher followed by the travel voucher, then Adam and Brian is not the same as Brian Adam. Or Adam Kira is not the same as Kira Adam. 1, 2, 3, 4, 12 in total. Because the order mattered. Anytime you hear the word arranged, order, we're talking permutations. So what formula do we use? We say 4 friends, 2 gifts. However, the outcomes are depending, so the order matters. So it's a permutation. So I would say 4p2. 4 friends, 2 things to give out. Order matters. 4p2. And again, I go to this equation, which is the same as the C equation without that bit, without the OR bit. So I say 4p2, 4 factorial over 4 minus 2 factorial. 4 by 3 by 2 by 1 over 2 by 1, 12. Another way of doing this is you could have said, I'm not going to solve it that way. I'm going to say, okay, let's look at the music voucher. And very often in probability, there's loads of ways of getting the same answer correctly. But just make sure the logic is right. I've got Adam, Brian, Kira, and Donna. And as for music, how many ways could I do that? Well, there's 4 ways. I could give it to Adam, Brian, Kira, or Donna. And with the travel voucher then, how many ways can I go after that? Well, I can give it to Brian, Kira, and Donna, assuming now that I'm not going to give it to Adam again, because you only get one of the 2. Okay, so this would be C, D, A, and this would be D, A, B, and this would be A, B, C. So I've got 1, 2, 3, 12 options in total, from AB on the top, this route, to DC on the bottom, the 12. That's another way of doing it. Okay, you could do it by the tree if you wanted. Now, let's see how this question comes into its own. A school student council needs to elect a female chairperson and a male chairperson. Ellen, Rachel, Beth, Sarah, Orla, Sheila, Brian, John, Stephen, and Matt. Well, hopefully they'd make it easier for us with all the names to know which is which. The students have chosen Beth and Matt as representative chairpersons, so they're gone. Beth and Matt. What is the probability that Stephen and Ellen fulfill these posts? Okay, the student council needs to elect a female and a male. So let's count how many females are left and how many males are left. Well, with Beth gone, there are 5 other girls. Girl 1 to girl 5. With Matt gone, as Matt is appointed chairperson, other boys are available for the deputy. The probability is chosen. There are 3 boys, B1 to B3. So, we've got girl 1, girl 2, girl 3, girl 4, girl 5. Boy 1, boy 2, boy 3. What they're saying is, what is the probability that a particular girl who will be chosen and a particular boy? Well, what's the probability that it's girl 3? We're not counting the boys here. We're just counting here. So what chance has girl 3 got? The same as everyone else. 1 in 5. For the boys, what's the chance that B3 has got? Same as everybody else. All the boys only, 1 in 3. Are they independent? Yes. Because if I choose girl 3, I can still choose any of these. It's not in any way linked. Or if I choose any of these, I can choose any of those. So because they're independent, it's 1 over 5 by 1 over 3. Ellen and Stephen, 1 over 5, 1 in 15. Now, this is a typical exam pattern. 5 girls and 4 boys are members of a social group. They wish to appoint a committee of 4 people to organise a group. How many different ways can the committee be formed under the following circumstances? If there are no restrictions, if there has to be at least 3 girls on the committee, or if there has to be at least 1 boy and 1 girl on the committee. Five girls, 4 boys, making committees. Girl 1, girl 2, girl 3, girl 4, girl 5. Boy 1, boy 2, boy 3, and boy 4. They wish to appoint a committee of 4 people. They wish to appoint a committee. A committee. Does it matter? You've got to find out here, does order matter? Does it matter whether boy 3 is chosen before girl 2 or after girl 2? No. Why? They're both on the committee. One isn't the treasurer and the other is secretary, or one is the president. They're both on the committee. So if they're both on the committee, the order doesn't matter. And if the order doesn't matter, it means we're talking about the letter C for combinations. How many different ways can the committee be formed under the following circumstances? If there are no restrictions. If there are no restrictions, how many people are there? Well, there's a total of 9. Okay? So no restrictions, a total of 9 people. How many do I want? 4. So there are 9 people. I want 4, and it's a combination. Because the order doesn't matter. So the answer is 9 factorial, 9 minus 4 factorial, 4 factorial. And whatever that turns out to be. That's if there are no restrictions. So if there are no restrictions, it's 9 people to choose from. 4 I want to pick. 126 different ways. Okay. Now, I want at least 3 girls on the committee. Well, if I want at least 3 girls on the committee, then I could either have 3 girls or 4 girls. Let's go with 3 girls first. How many ways could I get 3 girls on the committee? Well, if I want 3 girls on the committee, I'd have to pick 3 out of 5. Doesn't matter which ones I pick. And it doesn't matter if girl 3 is chosen before girl 4 or vice versa. The order doesn't matter. So if there are 5 to choose from, and I need 3, and it's a combination, that's the number of ways I can get 3 girls on the committee. Now, if I have 3 girls on the committee, I still can pick a boy. How many ways can I pick a boy? Well, 4 ways. I could pick boy 1, boy 2, boy 3, boy 4. Or I could say there are 4 boys to pick. I want 1, and it's combinations. I don't care the order. And 4C1 happens to be 4 as well. So that's 3 girls. But I could also have 4 girls on the committee. If I went with 4 girls on the committee, out of the 5, I'd want to pick 4 of them. Now, out of the 4 boys, I'd want to pick none of them. And 4C0 happens to be 1. So what I get here is, for the exactly 3 girls, I get 5C3, which is 5 factorial over all of this, which turns out to be 10. This leaves the remaining place available for a boy, but there's 4 ways of getting the boy: boy 1, boy 2, boy 3, or boy 4. So, and no matter what this combination is here, I can still pick any one of the boys, so it's that times that. So I end up with 40 ways in which I can have 3 girls on the committee. But I could also have 4 girls on the committee. So to get 4 girls on the committee, it's 5C4. Out of the 5, I want to pick 4 girls. So there's only 5 ways of doing that. And that should make sense because I could leave out either girl 1, 2, 3, 4, or 5. So at least 3 girls on the committee will be the 40 if there's 3 of them, and the 5 if there's 4 of them. That's 45 ways. So that's how you do that. Now we look at least 1 girl and 1 boy on the committee. Well, there's a few ways of doing this. I can go back here. I want at least 1. Well, at least 1 would be 1 or 2 or 3 or 4, and I could do the same here. What I could do instead is, what's the probability of no girl on the committee? and take that from 1, or no boy on the committee. So I'm going to start with, instead of 1 girl, 3 boys, 2 girls, 2 boys, 3 girls, 1 boy, I could work out all of those. But alternatively, it can be done more quickly by saying, what about 4 girls and no boy, and no girls and 4 boys? So 4 girls first and no boy. Well, 4 girls, if I wanted 4 girls on the committee, I would have to, forgive me, just drop the page here. If I want 4 of the girls to be on the committee, out of the 5, I want to choose 4. So 5C4. But I also want to have no boys. So out of the boys, I want none, and that's going to be 1. So 4 girls is just that. Exactly 4 boys. If I go with 4 boys, I want 4C4. Out of 4 of them, I want 4 of them. And 4C4, well, there aren't too many ways of doing that. I get to pick up the 4 of them. So there's only one way of doing that as well. So 4C4, one way. So one way of getting all boys, 5 ways of getting all girls. So committees with 4 girls, there's 5 of them. Committees with 4 boys is 1. Without restriction is 126. So if I take those from 126, I'm left with 120. That tells me ways of committees with at least 1 boy and at least 1 girl. So that's how it's done. The calculations are straightforward. It's just figuring out what am I looking for. Now, let's look at some calculations now when it comes to the binomial distribution. The binomial distribution is a lovely distribution where something is either one thing or another. So if the probability of rain during any particular league football match is 0.2, find the probability that a supporter who attends 7 matches in the season will watch exactly 3 matches in the rain. That's the sort of question you're going to be asked. Now, for many different events, the binomial says it's either one thing or another. So it either is sort of raining or not raining, a weekday or a weekend day, or summer or not summer. It can't be one of many options. You can't have a situation where it could be 1, 2, 3, 4, or 5, or 6. That won't work for the binomial. You could say it's either even or not even, or you could say it's a 6 or not a 6. It must be broken into 2 things. So very often we talk about win-lose, dry, wet, boy, girl. These are called Bernoulli Trials, where we talk about things either. So for the binomial distribution, you must have the following. You must have a set number of trials. There can only be 2 outcomes, one or the other, and trials must be independent of each other. And the outcome of probability is the same each time. So all of those things must happen for a binomial distribution. And there's this lovely formula here. The binomial formula for a number of successful trials is given by n(r), and that's really n(cr), p to the r, q to the n minus r, where p is the probability of success and q is the probability of failure or not success, and n is the number of trials and r is the number of successful trials. So let's go back to this question about the match. So using the Bernoulli trials, we say, what is the probability that, we'll go back to the question if I can find it, but I think it was probability of arranging exactly 3 matches. The person is going to watch 7 matches, okay? So the formula says n(cr), p to the r, q to the n minus r. So it says, on a given day, the probability that it's raining is 0.2. So p is equal to 0.2. If the probability of rain is 0.2, q is 0.8, because p plus q, the probability of something plus the probability of it not happening, has to equal to 1. So q is equal to 1 minus p, 1 minus 0.2, which is 0.8. So that's that. So if you have 7 matches and you would like exactly 3 matches, probability of it raining, then you'd say 7C3. The reason you say combinations is you don't want the first three necessarily to be wet. Any three will work. First, third, and fifth, second, third, and fourth, it doesn't matter. So the combination, the order doesn't matter as long as you get 3 out of 7. The probability of it raining on a given day is 0.2, and you want 3 days to be raining. And then the other is 0.8, and you want 4 of those to be dry. So that's how it works. So you can actually write down the answer to that question almost off the top of your head. Once you've got the formula here, you can say 7 matches, you want 3 to be wet. The wet is 0.2, 3 of those. The dry is 0.8, 4 of those. And you just work out the calculation. And it's 11.47%, which is really pretty impressive that we can do that almost off the top of our head. Here's the binomial expansion. It starts with p plus q squared, p plus q cubed. And we've seen that as Pascal's triangle, sometimes nice like that. So for example, if I were to run something 5 times, place bets 5 times, or 5 events or something like that, or the matches 5 times, there are, out of the 5, there's one way that they'd all be wet, and one way that they'd all be dry. But there's 5 ways here. 5 p q to the 4 will be 5p, 1 wet and 4 dry. Sometimes I think about these separately, and I would use the term b plus g. So let's imagine b is boy plus boy or girl, and let's say b plus g cubed. You'd get b cubed plus 3b squared g plus 3bg squared plus g cubed. So just imagine in a family of 3 children, if you were having 3 events, 3 births, 3 children, there's one way of having 3 boys, boy, boy, boy. There's one way of having 3 girls, girl, girl, girl. Now, you could have 2 boys and a girl, 3 different ways. You could have boy, boy, girl, girl, boy, girl, boy, boy. Because you could have the girl first, second, or third. And similarly here, you could have boy, girl, 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 boy, girl, and girl, girl, boy. You could have the boy first, second, or third. And really what's happening here is that this number here is telling you how many different ways in which you can get the same outcome of 2 boys and a girl. And that's your 3C1 or 3C2 in that case if you wanted 2. And if you wanted 2 boys, and here you wanted 3C1. Or if you were talking girls, you might say 1 and 2. But it turns out to be the same. 3C1 is 3, C2 is 3. So if I wanted, say, from 5 attempts here, and P was success and Q was fail, there's 5 ways of getting 1 success and 4 fails from 5 attempts. And in the middle, there could be quite a few ways. Now, I want to take a minute or two on the normal distribution. And I just want to explain that an awful lot of the questions are questions that you read from the tables. Okay, and there's a bit of reading on the tables, but they talk about a thing called a standard deviation and a mean. And they also talk about a thing called a standard error. And they talk about 2 types of standard errors. There's a thing called a standard error where they say it's sigma over root n. And there's also p, q over n, where they talk about the standard error of a proportion. And this is the standard error of the mean. Now I'm going to go through the logic here, but I'm going to do an exam question or 2 as well. And really what I want to explain here is that it's all about just seeing what they're asking and then saying, oh, this isn't individual values, this is a characteristic of a sample. For example, if they're saying the proportion of something in a sample is, then it's a proportion of a sample. And if it's a proportion of a sample, we're not talking about standard deviation, we're talking about this fella here, PQ over N. If they say we measure the weights of people, and of the 20 people we measured, their weights were such and such, how does that compare with another sample? Then we can see, are we talking about individual weights or are we talking about a sample? And I'll do these when I'm doing the questions. I want to read some questions to see, do we see what's really being asked? And then we can look up the tables. Now, the normal distribution, an awful lot of functions out there form a normal distribution. It could be exam marks, or it could be heights, or it could be speed at a certain junction or something like that. So it's a curve like this, and it's seen as symmetrical. And it's symmetrical in that it has an average value or a mean, and that's given as very often mu. Outside that, we've got things called standard deviations. So for the moment, I'm going to talk about individual values, and I'm going to talk about standard deviations and means. Okay? I'll deal with the other ones later in exam questions. But 50% of the curve is to the left and 50% is to the right. A standard deviation is a certain amount away from the mean, and here's one and here's another. And it says that a certain percentage of the curve is within that. 34.13% of the overall values fall between the mean and one standard deviation away. If you go out again to 2, you'll find that a certain percentage follows. And if you go out here to 2.5, you'll find another certain amount follows. So to a second standard deviation, it's 15.8%. So 15 and 34, that's quite a bit. It's nearly up towards 50, and then you move out all the way. And ultimately, the graph eventually hits the bottom. But there are people out there that are a few standard deviations from the mean, or values. Somebody might go through a junction really fast or really slowly. But by and large, they'd go through it at a certain stage. So let's look at how it works. The heights of female nurses has a normal height, normal distribution with a mean of this and a standard deviation of 4 centimeters. Heights of female nurses. Individual female nurses. Individual values, not a sample, individual values, we're talking about sigma. They have a mean of 165.4. Find the percentage of female nurses smaller than 160. So what we do is we draw the normal curve. It's always there for us. And we say that the average turned out to be 164 or 165.4. Now, the standard deviation was 4, so I'm going to go down 4 here and up 4 here. If I go down 4, I'm at 161.4. Here, I'm at 169.4. So these are individual heights of individual nurses. And I'm asked, what percentage of them are smaller than 160? Well, 160 on this is down here. And if I go back below this here, it looks to me is that, well, 50% are taller and 50% are smaller. So certainly, if we're talking about smaller than 160, I can rule out all of those. So 50% are gone already. And then one standard deviation, that's another 15% or 34%. So that's 84% are gone. So how do I find out how many are back here? So this is where the tables come in. So I say, okay, how far is 160 from 165? So how far is 160 from 165.4? But I'm not interested in how far it is. I'm interested in how far it is in terms of standard deviations. So in terms of standard deviations, the standard deviation is 4. So I'm going to take one from the other there, and I'm going to find out what that answer is. And the answer turns out to be minus 1.35. Now, it doesn't matter whether it's how many are smaller than that or taller than the equivalent up here, it doesn't matter. But I've got 1.35 standard deviations. So I'm now interested in finding how many are taller than that or smaller than that. So I go to the tables, and it's really important in the tables that I look at the graph. The graph of the tables here are a bit strange in that it's showing me the shaded area. So at 0, it's telling me that 50% of the people are up to that point 0. Whereas if I go to 1, down here, I get 84%. Now that should be reassuring. That's my 34% and my 50%. But I'm interested in 1.35. Now really I would have liked it if they had drawn the graph this way, because I was interested in the numbers below here. But actually I'll have to use the graph and look at the mirror image and the numbers above there. If that's 1.35 standard deviations, I must go up to 1.35 standard deviations here, because there's only one graph here and it seems to be drawing it this way. So I've got to go to not 1 standard deviation, but 1.35. So I go to the next page. Oh, sorry, it is here, great. I thought I was missing it. So 1.3 and across to 5. 9115, which is great. So this is telling me that by the time I get to here, I've picked up 91.15%. 91.15% of nurses have heights above this section, because that's the shaded area on this graph. So therefore, the remainder, taking that from 100, 91.15, that'll be what, 8.85% below that value there. So how does it get done? You look at how far is 160, the height you're interested in, from the mean. And I found that in terms of standard deviations. So it was 1.35. Using the tables, I found that that was 8.85%. And that's how I got that. Now, another way of looking at this question is, how tall are the tallest 10%? Now, I want the tallest 10%. Now, in this particular graph, here's the nurses again. I'm looking at the tallest 10%. 10% up here. Well, if I was using this graph, wherever it was, and I wanted the top 10%, the shaded area would have to be 90%. So I use the tables in a different way now. I'm looking for the point on the tables where the area is 90%. So I have to look in here, not here, because I don't know how far out it is. I have to look at where is there a 90. So 0.5, 0.8, 0.85. I still have to keep on going. Oh, look, 90 is around here. 0.8997 or 9015. This is really close. 0.8997. I could split it if I wanted, but 1.28. So it looks like at 1.28 standard deviations from the mean, that's where the top 10% kick in. But a standard deviation was 4 centimeters. So I should be able to get that by saying 1.28 times 4 centimeters is whatever that is. It's 5.4, plus the mean. So 1.28 by 4, whatever that is, that's about 5, is it? And I add it to the other and I get 170.52. So 170.52, that's the height. So that's how we do these tables. So let's see if we can see some questions on that. But I'll just show you, I wanted to show you how you would use that for a standard error question as well. So hopefully we can get that as well. I might start with that so that I make sure I have time. Okay. We'll start with question 8 from 2020. So the airline company Trans-Sky Airways has designed an aptitude test for people applying for trainee pilots. The aptitude test is scored out of 500 marks. The results are normally distributed with the mean of 280 and a standard deviation of 90. So we just look at this and we'll say (280), standard deviation and 90. So what I would do there is I would draw one standard deviation and 2, one standard deviation and 2, and add 90 and say that's 370 and that's 460. Take away 90, 190 and 100. And I'm more or less ready now to sort of get a feel for what the answers are. The top 25% of people taking the aptitude are invited back, find the minimum mark on the test. So we're looking here at individual trainee pilots. So we're talking about sigma. We're told has designed an aptitude test. The aptitude test is scored. The results, the top 25% of people are invited back, find the minimum mark needed in order to be invited back. Well, if they're talking about the top 25%, and this is 50% here in the lower half, and this is the top 50%, and if this is 34% in the next one, that would only leave 16. So it looks like we're looking at a bit like here. That would be about 25%. I would say it's less than one standard deviation away from the mean. That's my sort of answer that I'm thinking of getting. But I want, in the tables that I look up, 25% to be left over. If I want 25% to be left over, I'm looking for 75% to be included. So I now go to the tables and I say, if I want the shaded area to be 75, how do I get that 75? So I come down here and I say 0.75, looks like there. And that says 0.68 or something like that, 0.68. So it says 0.68, not a full standard deviation. 0.68 of a standard deviation is where this breaks off. Now we have to go back into the question. So we said 0.68 of a standard deviation. Standard deviation was given as 90, so 0.68 times 90. Above the mean, so the mean is 280. 280 plus this. And whatever that turns out to be, that's the top 25% of the people. So that's the first part. The second part, anyone who scores above the 40th percentile can resit the test later. So here we've got the graph again. And we say if you're above the 40th percentile, so 40th percentile, well, the bottom, that's the top 100. So that's the 50th percentile here, 50. 40 would be back here, 40%. This is the bottom 40%, just this area here. So how do you find the bit where you've got 40%? Well, you go to the shaded area again, and in this case you want the shaded area just to equal 0.4. And you look and you say, I can't find it. It starts at 0.5 and it goes up to whatever. So how do I do that? Well, I'm looking for the bit that's here. Maybe I could look for the opposite bit that's there. If I could find the 60 percentile rather than the 40, I could find it. And then use the same gaps. So I'm going to go to see where there's a 60. See where it becomes 6 for the first time. and it seems to be around here, 0.25 or something like that. So it looks like a small amount of the, let me draw that a little bit neater again, or let's draw it again. There's a lot going on there. I think it was 280, and this was maybe 190, and that was 34%, and this was 50%, and I just wanted this to be about 10%. So just about 10% here. So this bit here is the 40th percentile. So it's not a full standard deviation, nowhere near it. Actually, it turned out to be only 0.25 of one. So it's 280, and because I'm going in the reverse direction, minus 0.25 of 90. So whatever that turns out to be. So 25 of 90 is 22.5 or something like that, and it turns out to be 257.5. So 257.5 is the minimum point at which you're invited back. Eileen scored 260. Was she allowed back? Well, 260 is greater than 257.5, so she was. Now, when we did these graphs here on the normal curve, and I should have explained that here, I'll draw another normal curve, and these are obviously all over your chapter on probability on the binomial. But if I go down 1 and 2, 1 and 2, if I go down to 1.96 standard deviations, not to 2, I actually end up with a lovely number of 2.5% here and 2.5% here. In other words, I end up with 95% in the middle. So very often you hear the term plus or minus 1.96 standard deviations, or sometimes standard errors. But basically you can see that 95% of the graph falls between the two. So that's why that's an important base. If you want it to go down to 99%, it's plus or minus 2.58. You have to go all the way down to about here on both sides, just to leave 1% in both sides. Okay, explain the relevance of the scores 1.96 and minus 1.96. So you really just have to explain that they're interesting because they leave 2.5% here and 2.5% here. And if you were to look up the numbers there, and you were to go down to 1, 1.9, and across to 6, you can see 0.9750 or 97.5%, leaving 2.5% here and 2.5% there. Now, this is where you have to be just a little bit, I suppose, sharp, and that's a Trans-Sky Airways surveyed 2,500 of its passengers about a new service it wants to introduce. The variable P is the proportion of respondents in the survey who said they would use the service. The radius of the service is given by 0.01568. Now, where the value of P is this. Really what they're saying is if the proportion of something is P, then the standard error, instead of being sigma, it's actually PQ over N, or P1 minus P over N square root. And if that's the size of the standard deviation, in this case the standard error, 1.96 plus or minus on both sides equals 0.1568. And now you've got to calculate what they are. Can you solve for P? And hopefully you're able to solve for P. You can take this number over, you can square this to unsolve it, and the number they chose in the sample was 2,500. So everything is known there, you just have to solve for P. So have a look at that question on the exam. You can see it there, it's 2,000, and just look at how it solved it. It's more I want you to figure out which formulae to use rather than the actual calculations. So let's look at this now. The weight of the airline passengers' carry-on luggage is normally distributed with the mean of 12. So the weight of somebody's luggage has a standard deviation of 12. The airline recently introduced a fee for non-carry-on luggage. After the fee was introduced, the airline expected the mean weight to change. They selected a random sample of 80 passengers and weighed their carry-on luggage. So what's happening here is they had a sample, they took a sample, and this is really important that they give these hints in the question. They took a sample where n was equal to 80, and the sample mean was 13.1. So let's call this mu for a moment. Well, or even x bar if we want. The sample mean is 13.1. And the sample standard deviation they got was, say, 4.5. Now, it used to be, test the hypothesis at the 5% level that the mean weight of the carry-on luggage has changed. The weight is normally distributed at a mean of 12. Now, it used to be 12, but they got 13.1 with the standard of 4.5. Now, I'm just going to draw this for a minute and show you what it is and what it's not. And this is really important. They, before, said that it used to be 12 was the standard weight, and it moved around a lot. People had different weights. But if you go and you ask individual what their weights of their luggage are, it's going to go all over the place. But if you think about it, if you get 4 people, 10 people, 20 people, and you get them in a sample, you'll find that what happens is that the more and more you get in a sample, the more some of the heavy weights will compensate with the lower weights, and you'll get an averaging. In this particular question here, they took a sample of 80 passengers, and they found the average of the sample was 13.1. Not one person with 13.1, but the average of 80. And this is called a standard error. So instead of using sigma, we use sigma over root n. Because really what happens is, if I can draw it sort of a bit like this. If I went into a particular class of people, in school class, and I looked at their heights, they would vary. And there'd be some tall and some small, and that's the way it would be. But if I went into a school and said, what is the average height of a particular 6th class? And they told me it was a certain height. And then what's the average height of a particular 6th class in the next school and the next county and whatever? I would find that that pattern would be far more around the middle, because all of the small and all of the very tall would all be averaged out. Because if there's a tall person, well, he or she is balanced by the 20 or 30 others in the class. So the bigger the class, well, the bigger the class size, you should start getting graphs like this. And depending on the actual size of the actual population, the bigger it would be. So if you took the average of all 6th years in the country, then you'd find that it's really, not going to move at all, because it's just one value. If you took the average of, say, you're taking people from Munster, the people from Leinster, you wouldn't see any particular reason why there'd be a difference there. So effectively what we're happening here is, really we're talking about a much tighter curve, because this is a sample of 80 people. So it's not like individual weights, it's the averages of. So the standard deviations have got a lot tighter. They're no longer sigma, but sigma over root n. So let's look at how that question really comes out. The way I would answer that is, we got 13.1. That's higher than 12. So the standard error is basically, it's not sigma anymore, it's sigma over root n. Now, sigma over root n, all I have to do is calculate the square root of 80. So sigma was 4.5 over the square root of 80. I'll just get that calculator for the moment, and I'll say, bear with me a sec. I can find a calculator here, I'm sure I can. Turn it around, 80 square root 8.9, and I'll say 4.5 divided by 8.9. So 4.5 divided by 8.9 looks like 0.5056. So the standard error I'm talking about is now 0.5056. So my graph is now, how far is 12 and 13.1 apart if the standard error is 0.5056. If sigma over root n is 0.5056, two of them would be about 1, would bring me to about 13, so that'll be about, two of them would bring me to there, 13, and 13.1 I think was the average weight, so 13.1 minus 12 over 0.5056. So I look that up and I say 1 divided by 1.1 divided by 0.5056 is 1.798. And I work out then what percentage are above that or below that. So that's how those questions are done. The company bus carries a total maximum weight of 3,000 kilograms, and it's a similar there for that. It's a similar type of approach. Okay? So just know whether you're using the proportions or you're looking at the standard errors. The same graph applies. You're going to figure out, how many are above it, how many below it, or use the graph to say how many are in it. So finally, just a few quick ones to call off. This is a class consists of 12 boys and 8 girls. 12 boys, 12B and 8G. 2 students are selected at random from the class. What is the probability that the 2 students will be a boy and a girl in any order? In any order? Order doesn't matter. It's combinations. Okay? So I want 1 boy and 1 girl. Out of the boys, there are 12. I want 1 of them. Out of the girls, there are 8. I want 1 of them. For each of these, this can happen. So 12C1 by 8C1. And that's it done. 4 students are selected one at a time at random from the class. What is the probability that the first 3 students selected will be boys and the 4th will be a girl? Now, the first 3 will be and then. The order matters. The order matters, so we say first 3 will be boys. So the first one being a boy, the second one being a boy, and the third one being a boy. Well, the first one being a boy would be 12 over 20. Because you can't pick the same boy again, you've got to reduce it then to only 19 left. And there's 11 boys left. Then there's 10 and there's only 18 left. And then you want a girl and there's 8 of those and there's 17 left. And that's how that will be done. An examination paper is made up of 2 sections. Section A, 7 questions. A has 7 questions and B has 8 questions. The paper contains the following instruction. From section A, you must answer question 1 and any 3 others. Well, if you have to answer question 1, it's certain. There's only 6 left. So A has 6 left and B has 8 left. How many ways can you answer 3 from section A? The order doesn't matter. There are 6, you want 3. In here, I think you've got to answer 4 questions from part B. 8 questions, you've got to answer 4, multiply. So, finally, just think about the difference between combinations and permutations. Just think about this. Let's say there's the Olympics, it's the 100 meters freestyle, and you're asking how many different ways can the results be. You will say that there are 8 lanes and there are 3 winners in that there's gold, silver, and bronze. How many different outcomes can there be? Well, if you want to say how many different ways can people get medals, in that case, I think you might say that the gold is different from the silver and the silver is different from the bronze. So in that case, there are 8 people. You do want 3, but it's a permutation question because the order matters. It matters whether Ireland comes first, second, or third, or Spain, or Germany, or France, or whatever. Whereas if it was just there are 8 people in the primary school race in junior infants, and the first 3 get lollipops, or they get whatever, cake or bun or whatever it is, or whatever, then it might be 8C3 who got lollipops, without counting necessarily who was in first, because it was a bit chaotic anyway. So that's the sort of idea. Hopefully that helps. So, Leishin, I just wanted to say thank you so much for your time today. Thank you for being with me. I really hope that some of the questions helped and that you filled in some of the gaps in your knowledge in the 4 areas we covered today. Wish you the very best with your Leaving Cert results, whether you sit the exam itself or whether you go for calculated grades, and that you filled in and you're more confident to give it a go and to do the best you can. So, slán go fóill, Ganari live, and have a great summer when it comes. Slán go fóill.